The Nebraska Sandhills in January of 1900 were a brutal canvas, painted in shades of white and gray. The cold wasn't just a chill, it was a predatory force that seeped into bones and froze breath in midair. Inside Jonah Miller's newly constructed cabin, the battle against the elements was a losing one. Ice crystals formed a delicate, deadly lacework on the interior walls, mocking the meager warmth radiating from a fire that stubbornly burned a mere 3 feet from his water bucket, the contents of which remained stubbornly solid. Jonah had followed every piece of advice handed down through generations of prairie settlers. He had meticulously built his homestead according to the established wisdom: tight log walls chinked with mud, thick sod reinforcing the structure, and a stone fireplace intended to be the heart of the home. Yet, the heart was failing. By February, Jonah had depleted 4 cords of precious wood, a fortune in labor and transport, and still, his family huddled together, shivering their way through the long, unforgiving prairie nights. Across the seemingly endless grasslands, other homesteaders were facing the same grim reality, their by-the-book houses proving to be flimsy defenses against the relentless winter. They were failing gradually, their hopes and resources dwindling with each passing sub-zero day. Over the next 2 years, while others clung to familiar but failing methods, Jonah quietly experimented with a forgotten technique, a method involving a material that everyone else relegated to the realm of livestock: straw. He noticed something critical. His straw bale house maintained a consistent temperature 30 degrees warmer than the traditional log cabins in the area, all while consuming only half the wood. What was the secret? What had he understood about heat retention and insulation that every other prairie builder had completely and disastrously overlooked? The sandhills stretched endlessly under the pale, almost mocking, March sky of 1898. It was a landscape of rolling grasslands, sparsely populated with the skeletal silhouettes of cottonwoods clinging to life in creek beds. An occasional windmill, its blades a blur against the horizon, was the only sign of human intervention in this vast, untamed expanse. This was emphatically not timber country. The nearest railroad depot, a lifeline to the outside world, lay 40 miles east in Broken Bow, and every stick of milled lumber had to be painstakingly hauled by wagon across treacherous sand roads that dissolved into impassable quagmires during spring storms or shimmered with mirages in the relentless summer heat. What thrived here, what defined this landscape, was grass, endless, undulating waves of it. It turned the hills into a sea of bronze in the autumn, hiding the sandy soil that made this country both remarkably fertile and incredibly treacherous for anyone foolish enough to attempt building a permanent home. The Homestead Act, a beacon of hope for land-hungry Easterners and immigrants alike, had thrown open these lands to settlement, promising 160 acres of land to any family willing to prove up their claim by constructing a dwelling and cultivating the ground for a period of 5 years. By the late 1890s, families were scattered across the region like seeds scattered on the wind, each struggling to wrest a living from soil that, while excellent for growing hay, offered little in the way of traditional building materials. The closest thing to local stone was found in scattered creek beds, sometimes 20 miles apart, and even the hardiest cottonwoods rarely grew thick enough to provide proper house logs. Faced with these limitations, most settlers reluctantly fell back on the 2 construction methods that frontier wisdom, however flawed, had always recommended: log construction, where timber could be scavenged, or sod houses, where it could not. The Gunderson family, whose claim lay just 3 miles south of what would eventually become Jonah Miller's homestead, had spent their entire first summer in Nebraska engaged in the backbreaking labor of cutting sod blocks from the creek bottom. They stacked them like oversized, clumsy bricks to form walls a seemingly impenetrable 3 feet thick. The work was truly brutal. Each sod block weighed a staggering 40 pounds when wet, and the finished house, from a distance, looked solid enough to withstand the test of generations. The reality, however, proved to be painfully different. The sandy soil of the upland sandhills lacked the dense root structure that gave prairie sod its stability in other regions. By their second winter, the Gundersons watched in dismay as their walls settled unevenly, gaping cracks appearing along the corners. Through these openings, the relentless prairie wind drove stinging snow directly into their kitchen. The south wall developed a distinct lean, a disturbing angle that worsened with each passing spring as the alternating cycles of frost and thaw heaved the foundation and the summer heat dried the sod blocks into crumbly, useless earth. Mrs. Gunderson spent countless hours each week desperately rechinking the gaps with fresh mud, fighting a losing battle against walls that seemed determined to revert back to the prairie from whence they came. Those settlers with a little more money, or perhaps better connections back east, attempted to import lumber, but the prohibitive cost of transportation proved to be crippling. The Holbrook brothers, for example, had hauled enough pine boards from Grand Island to frame a proper house, spending nearly $200 on materials alone, a small fortune in those days, before even factoring in the weeks of grueling wagon trips required to transport it all. Their finished home was undeniably tight and square, built according to patterns that any carpenter back east would have immediately recognized. However, the thin walls and single-layer board construction offered pathetically little protection against the fierce prairie winds that could, and often did, drop temperatures by a shocking 30 degrees in a single hour. The Holbrooks burned through 6 cords of wood their first winter, scavenging cottonwood from creek beds and buying coal from town whenever they could scrape together the funds. Even with this constant effort, their children were forced to sleep in their wool coats on the coldest nights, and ice regularly formed on the inside of their windows, despite the fact that a fire burned constantly in the kitchen stove. The house was, on paper, everything that frontier building guides said it should be. Yet, it utterly failed to provide the basic level of comfort and protection that any family needed in order to survive the harsh Nebraska winters. These failures were not isolated incidents. They were not unique to the Sandhills. Across the vast expanse of the Great Plains, homesteaders struggled with the same fundamental problem. Building methods developed in the forested regions of the East simply did not translate to the realities of a grassland environment. Traditional log construction required trees that simply did not exist in any significant quantity. Sod building demanded specific soil conditions that varied wildly from place to place, and importing lumber created financial burdens that could bankrupt a fledgling farming family before they even had a chance to bring in their first harvest. Into this landscape of struggle and disappointment came Jonah Miller in the spring of 1899, a man whose background and experiences had uniquely positioned him to see possibilities where others only saw limitations. He had grown up on a prosperous grain farm in southeastern Pennsylvania, where his father and grandfather had managed extensive hay operations that provided feed for dairy cattle through long, demanding winters. The Miller farm boasted a massive barn, a testament to ingenuity, built by German immigrants in the 1750s. Its walls were ingeniously filled with loose straw packed tightly between heavy timber posts. The entire structure was meticulously designed to store enormous quantities of hay while simultaneously keeping it dry and well insulated through months of relentless cold weather. Jonah had spent his youth learning the intimate properties of hay and straw, gaining a deep understanding of how different grasses behaved when cut, dried, baled, and stored. He knew that wheat straw, when properly cured and protected from ground moisture, could last for years without rotting. He had witnessed firsthand how loose straw, properly contained within barn walls, created an effective insulation barrier that kept livestock comfortable even when outside temperatures plummeted well below zero. Most importantly, he had observed the arrival of the new mechanical hay balers that began appearing in Pennsylvania during the 1880s. These ingenious machines compressed loose hay into tight, rectangular blocks that could be stacked and handled almost like building stones. When Jonah first surveyed his Sandhills claim that first spring, he saw what every other settler saw: seemingly endless grass, sandy soil, a frustrating scarcity of timber, and the daunting challenge of creating shelter from materials that seemed woefully inadequate for permanent construction. But his unique Pennsylvania experience also allowed him to perceive something that others completely missed. The prairie grass that locals routinely cut for hay produced bales that were remarkably uniform in size, tightly compressed, and available in quantities that utterly dwarfed the meager lumber supply available from the nearest sawmill. The idea came to him gradually, not as a sudden flash of inspiration, but as a logical extension of what he already understood about straw and insulation. If German barn builders could create warm, stable walls using loose straw packed between posts, why couldn't compressed bales serve the same function even more efficiently? If Pennsylvania farmers could successfully store tons of baled hay in structures that lasted for decades, why couldn't those same bales become the structural components of the house itself? The first time Jonah tentatively mentioned this radical possibility to his nearest neighbors, the reaction was immediate and dismissive. Tom Brennan, whose family had been engaged in a seemingly endless battle with their failing sod house for the past 3 years, actually laughed out loud at the suggestion. "That's just barn thinking, Miller," he scoffed. "If you want to live like livestock, you go right ahead, but don't expect any of us to follow you down that foolish path." Sarah Holbrook, never one to mince words, was even more direct in her disdain. "Straw is what you put under animals, Miller. People live in real houses, made of real materials. Wood and stone have kept families alive for centuries. Grass won't." The skepticism ran deeper than simple conservatism or resistance to new ideas. These were pragmatic people whose very survival depended on making sound, rational decisions about shelter, and they had absolutely no patience for experiments that might fail catastrophically when the inevitable winter winds began to howl. They had all seen what happened to families whose houses collapsed, or burned to the ground, or simply proved woefully inadequate when the weather turned harsh. The stakes were simply too high for innovation that hadn't been rigorously proven by generations of practical use. But Jonah Miller had seen those generations of use, albeit in a different context. He simply needed to translate that knowledge to the unique challenges of the Nebraska sandhills. He quietly began planning his experiment, meticulously considering every potential obstacle and designing solutions to overcome them. The first critical test was not related to wind or cold. It came from water. Spring rains in the sandhills were notoriously unpredictable, capable of transforming normally dry, sandy creek beds into raging torrents and creating large, stagnant pools in low-lying areas where winter snow had stubbornly lingered. Jonah Miller carefully observed the water table as it rose and fell in response to the unpredictable weather, meticulously noting how moisture moved through the loose, sandy soil that made this region both relatively easy to cultivate and incredibly treacherous to build upon. His upbringing in Pennsylvania had instilled in him the unwavering belief that water was the mortal enemy of any structure, but especially of one constructed from organic materials. His grandfather's stone foundation barn had stood strong for nearly 150 years because the original German builders had understood a fundamental principle: keep wood and straw elevated and away from ground moisture, and they would outlast the families that built with them. Allow them to come into contact with damp earth, and rot would inevitably set in, destroying even the strongest timbers within a decade. This critical lesson was reinforced when Jonah examined what remained of earlier settlers' attempts at unconventional building. 3 miles northwest of his claim, he discovered the rotting remnants of a hay storage shed that Otto Kinski had hastily built the previous autumn. Kinski had simply stacked loose hay directly on the ground, covering it with a canvas tarp and naively hoping for the best. As expected, spring moisture had wicked up through the bottom layers, creating a perfect environment for decay. By May, the entire bottom course of hay had transformed into a mass of black, soggy compost that attracted vermin and gave off the sickly sweet smell of fermentation. This disheartening failure pointed directly toward a crucial solution. If ground contact inevitably destroyed organic building materials, then elevation was absolutely essential. But elevation alone would not be enough. The sandy soil of the sandhills presented unique challenges that demanded specifically adapted techniques. Jonah began by carefully studying the water patterns around his chosen building site. He deliberately selected a gently sloping rise that would naturally shed rainwater, carefully avoiding both the low spots where water tended to collect and the exposed ridges that bore the full brunt of the relentless prairie winds. Then, he began to dig, not for a traditional basement, but for a meticulously designed foundation system that would completely sever the connection between his future bale walls and the moisture-laden earth below. The foundation trenches, dug with painstaking precision, extended down 3 feet, following the exact outline of his planned house, with additional extensions at each corner for added stability. Into these trenches, he carefully placed a layer of creek gravel, meticulously sorting the stones to include a range of sizes, from egg-sized pebbles down to coarse sand. This carefully graded gravel bed would serve as more than just simple support. It would act as a sophisticated drainage medium, capable of absorbing and channeling water away from the structure above, preventing it from ever reaching the straw bales. On top of the gravel, Jonah carefully laid flat limestone blocks that he had hauled, one back-breaking stone at a time, from outcroppings along the Middle Lou River, 20 miles to the east. Each stone was roughly 18 inches wide and 8 inches thick, creating a perfectly level platform that rose 15 inches above the surrounding ground level. The limestone served a dual purpose. It provided a stable and durable base for wall construction, and its naturally porous nature allowed any incidental moisture to evaporate rather than accumulating beneath the building materials. The truly critical innovation came in the form of a sophisticated moisture barrier system. Jonah had witnessed too many frontier buildings fail because the builders had naively assumed that solid materials would naturally resist water infiltration. Instead, he deliberately created what Pennsylvania barn builders referred to as a breaking layer, a carefully designed interruption in the capillary action that could draw moisture from the soil into the organic materials above. On top of each limestone block, he painstakingly placed a thick oak plank that had been thoroughly coated with pine tar and carefully sealed at the ends to prevent moisture intrusion. These planks, each 2 inches thick and 8 inches wide, formed a continuous sill that would support the bottom course of bales while preventing any direct contact between the straw and the stone. The tar coating was absolutely essential. It created an impermeable, waterproof barrier that moisture simply could not penetrate, even if it somehow managed to work its way up through the gravel and limestone layers. The drainage system extended far beyond the immediate perimeter of the foundation itself. Jonah carefully dug shallow trenches radiating outward from each side of the house, creating engineered channels that would efficiently carry rainwater away from the building site before it could even begin to pool against the foundation walls. These trenches meticulously followed the natural slope of the land, dropping precisely 1 inch for every 10 feet of length to ensure positive drainage even during the heaviest spring storms. The trenches themselves were carefully filled with smaller gravel and then topped with sod, creating what appeared to be natural swales, but actually functioned as a meticulously engineered water management system. During periods of heavy rainfall, water would naturally flow into these channels and away from the building site rather than collecting around the foundation where it could eventually find its way into the structure above. This sophisticated approach reflected knowledge that Jonah had absorbed during childhood visits to his great-uncle's mill in Lancaster County. The mill foundation had been expertly constructed by Moravian craftsmen in the early 1800s using techniques that kept the intricate wooden machinery perfectly dry even when the mill race was running at full capacity just 20 feet away. The key, he had learned, was understanding water not as an enemy to be simply resisted, but as a powerful force that could be skillfully directed and meticulously managed. When Tom Brennan stopped by in June to observe the progress of the foundation work, his skepticism was painfully evident. "You're building a stone castle for a hay house, Miller," he declared, shaking his head in disbelief. "All that digging and hauling. You could have framed a proper cabin with far less work." But Jonah had calculated the costs differently. The stone and gravel had cost him only labor and the rental of a wagon for hauling the limestone. A comparable foundation constructed using imported materials would have required hundreds of board feet of treated lumber at prices that could easily consume a homesteader's entire first-year budget. More importantly, Jonah was carefully building for specific conditions that his neighbors had not yet fully grasped. The sandhills presented a unique combination of challenges: sandy soil that drained quickly but also shifted unpredictably, extreme temperature swings that could easily crack rigid foundations, and moisture patterns that varied dramatically between wet springs and dry summers. His elevated stone foundation system was meticulously designed to handle all of these variables, while simultaneously providing a stable, level platform for the experimental wall system he planned to build above. The real test of his design came in early July when a 3-day storm dumped nearly 4 inches of rain across the region. Water poured off the foundation stones and flowed smoothly and efficiently through the drainage channels, leaving no standing water within 50 feet of the building site. Meanwhile, the Holbrook family spent 2 grueling days desperately bailing water from their wood-framed house, where inadequate foundation drainage had allowed rainwater runoff to collect against the walls and seep through gaps in the floorboards. When the storm finally passed, Jonah meticulously measured moisture levels in his foundation stones using a simple test that his grandfather had taught him. He carefully placed drywood shavings against the stone surface and checked for any signs of dampness. After 24 hours, the limestone blocks showed absolutely no sign of retained moisture, while the gravel bed had drained completely within 6 hours of the rain stopping. The foundation system was clearly ready to support whatever Jonah planned to build above it. More importantly, it had already proven, beyond any reasonable doubt, that water could be effectively managed through careful design rather than simply endured as an inevitable hazard. The individual techniques were not necessarily revolutionary, but their specific application to straw bale construction represented a crucial step toward making his experiment viable for long-term habitation. The bales finally arrived in August, delivered by wagon from Heinrich Zimmermann's farm 6 miles south, where a brand-new mechanical baler had been churning prairie grass into compressed, rectangular blocks since the early summer. Each bale measured 18 inches high, 14 inches wide, and 36 inches long, weighing approximately 40 pounds when properly cured. Jonah had initially ordered just 50 bales, intending to carefully test the stacking and handling characteristics before committing to full wall construction. The first significant challenge was achieving perfectly level courses without the uniform dimensions that sawn lumber provided. Unlike manufactured materials, each bale varied slightly in density and in its exact measurements, requiring constant adjustment and careful attention to detail in order to maintain plumb walls. Jonah developed a clever technique using wooden wedges driven between the bales to eliminate gaps and ensure tight joints. Where bales were slightly undersized, he painstakingly packed loose straw into the voids, compressing it firmly by hand until the wall surface remained perfectly flat and solid. The stacking pattern closely followed masonry principles that Jonah had observed in Pennsylvania stone construction. Each bale was laid like a brick, with vertical joints offset from the course below, creating an interlocking strength that effectively prevented the walls from separating under lateral stress. The bottom course sat directly on the tar-coated sill planks, with each subsequent layer pressed firmly against the one below until the walls reached 8 courses high, creating a finished wall thickness of 12 feet. But thickness alone did not guarantee exceptional thermal performance. The truly critical factor was minimizing air movement within the wall system. Jonah had learned from his grandfather that dead air, air that was perfectly still, was nature's most effective insulator, but only when it remained truly still. Moving air carried heat away through convection, effectively turning potential insulation into a thermal drain. The key, he realized, was creating sealed air pockets that could not participate in heat transfer. This guiding principle dictated the plastering process that began in September. Jonah carefully mixed local clay with chopped straw and water, creating a thick, tenacious mud plaster that could be effectively worked into every gap and surface irregularity of the bale walls. The plaster served multiple crucial functions. It sealed the straw against air infiltration, created a smooth, uniform surface for interior finishing, and added a layer of structural cohesion that transformed loose agricultural waste into a solid, monolithic building system. The exterior plaster was meticulously applied in 2 coats, each approximately 1 inch thick. The first coat was worked deep into the surface texture of the bales, filling every void and creating an airtight barrier. After this base coat had dried for a week, Jonah applied the finished coat, carefully mixed with lime that he had painstakingly burned from shells collected along the Platte River. The lime plaster created a hard, weather-resistant surface that would effectively shed rain while simultaneously allowing moisture vapor to escape from within the wall system, preventing the buildup of damaging condensation. Interior plastering followed the same 2-coat process, but with different materials specifically chosen for their performance in heated indoor conditions. The base coat used the same clay and straw mixture as the exterior, but the finish coat incorporated fine sand and additional lime to create a smooth, light-colored surface that would effectively reflect lamplight and resist the soot accumulation that plagued so many frontier homes during the long winter evenings. The thermal testing began naturally as autumn temperatures started to drop noticeably in October. Jonah carefully built small fires in his kitchen stove, meticulously measuring fuel consumption and interior temperatures using methods his father had taught him for monitoring barn conditions during harsh Pennsylvania winters. A simple thermometer hung on the north wall, carefully positioned away from direct heat sources, while another thermometer, placed just outside the north window, recorded the ambient air temperature. The results dramatically exceeded his most optimistic calculations. On a night when outside temperatures plummeted to a bone-chilling 20 degrees Fahrenheit, the interior temperature in the Bale house stabilized at a comfortable 58 degrees Fahrenheit, with only a modest fire burning in the kitchen stove. By comparison, the Holbrook family reported interior temperatures of a frigid 32 degrees Fahrenheit the same night, despite burning a larger fire continuously throughout the evening. Even more significantly, the Bale house retained heat long after the fire had died down completely. When Jonah allowed his stove to burn out entirely at bedtime, the interior temperature dropped only 8 degrees by morning, while outside temperatures fell another 12 degrees before dawn. The thermal mass effect of the thick walls was clearly storing heat during active burning periods and then slowly releasing it throughout the night, maintaining remarkably comfortable conditions with a minimal input of fuel. The fuel economy became even more apparent through precise measurements. During a typical week in November, with daytime temperatures ranging from a chilly 30 degrees Fahrenheit to 45 degrees Fahrenheit and nighttime lows fluctuating between 15 degrees Fahrenheit and 25 degrees Fahrenheit, Jonah burned just 1/4 quart of cottonwood to consistently maintain interior temperatures above 50 degrees Fahrenheit. The Holbrook family, heating a comparable floor area in their frame house, consumed a full quart of wood during the same period while managing to achieve significantly lower average interior temperatures. This dramatic performance differential reflected the fundamental physics of heat transfer through different wall systems. The 12-inch Bale walls created a substantial insulation barrier that slowed conductive heat loss, while the sealed air spaces within the straw effectively eliminated the convective heat transfer that plagued structures built with gaps and air leaks. The thick walls also provided significant thermal mass that moderated temperature swings, preventing the rapid heat loss that occurred in thin-walled buildings as soon as the heating sources were reduced. Word of these remarkable results slowly spread through the informal networks that connected the scattered homesteads across the region. Martha Brennan casually mentioned to Sarah Holbrook that the Miller family seemed unusually comfortable during the particularly severe cold snap in late November. Tom Brennan grudgingly admitted that he had stopped by Jonah's place during a blizzard and found the interior warm enough for short-sleeve comfort, with no fire even visible in the stove. The initial skepticism began to slowly shift toward curiosity as winter deepened and fuel costs continued to mount for families relying on conventional construction. Coal delivered from Grand Island cost a prohibitive $2 per ton, while cutting cottonwood from the creek bottoms required days of backbreaking labor that could have been spent on other essential tasks. The Miller family's obvious fuel efficiency represented real, tangible savings that could easily determine whether a homesteading family managed to survive their first winter with resources intact for spring planting. By December, several neighbors had cautiously visited Jonah's homestead to examine the Bale construction more closely. They found walls that felt surprisingly solid when knocked upon, surfaces that showed no signs of settling or deterioration, and interior conditions that remained remarkably comfortable even when outside winds drove stinging snow directly against the windows. The experimental building had clearly become a functional demonstration, challenging long-held assumptions about what materials could provide adequate shelter on the Great Plains. The accumulating thermal performance data was building a compelling case for techniques that utilized abundant local materials to achieve superior results with less labor and at significantly lower expense than conventional methods required. But the ultimate test was still yet to come, when the full force of prairie winter would determine whether this innovative approach could truly withstand the harsh conditions that had already defeated so many families attempting to establish permanent homes in this unforgiving landscape. The roof system presented a unique set of challenges that no frontier building manual had ever adequately addressed. Conventional wisdom typically assumed that walls were either solid timber, capable of bearing enormous loads, or stone masonry, which could support virtually any roof design. Bale walls, with their compressed organic structure, fell into neither category, requiring innovative structural solutions that distributed weight evenly while also accounting for the compressed nature of the supporting material below. Jonah had observed numerous roof failures throughout the Sandhills during his first 2 years of residency. The Gunderson family's sod house had developed a dangerously deep sag along the ridge beam when heavy snow accumulated in February, while the Kreminski cabin had lost an entire section of shingles during a spring windstorm that caught the extended eaves and twisted the roof structure beyond its designed capacity. Both of these failures stemmed from a fundamental misunderstanding of how loads moved through different building systems. Traditional gable roof construction concentrated the entire roof load on 2 opposing walls, with the ridge beam transferring the weight down through the end walls to the foundation. This approach worked reasonably well when the walls were constructed of thick logs or solid stone that could bear concentrated loads without significant deformation. But bale walls, despite their exceptional thermal performance, could compress under concentrated point loads or buckle if stressed unevenly along their length. The solution, Jonah realized, lay in studying the barn construction techniques that he had carefully observed during his Pennsylvania childhood. German immigrants in Lancaster County had built massive hay storage barns using hip roof designs that distributed loads across all 4 walls rather than concentrating stress on just 2 gable ends. These barns were capable of carrying enormous weights of stored hay and heavy equipment while maintaining remarkable structural stability for decades without requiring any major repairs. Adapting this principle to residential construction required careful attention to load path engineering. Instead of a traditional ridge beam running between 2 end walls, Jonah carefully designed a hip roof system with 4 triangular roof sections converging at a central point. This unique configuration transferred roof loads down through rafters that bore against all 4 walls simultaneously, effectively spreading the weight evenly across the entire perimeter of the building. The critical structural element in this design was the top plate system that crowned the bale walls. Jonah carefully selected straight-grained oak planks, each 4 inches wide and 2 inches thick, running continuously around the entire perimeter of the building. These planks were skillfully notched at the corners and secured with wooden pegs driven through overlapping joints, creating a rigid ring that could efficiently distribute loads. While bracing the walls laterally, this design ingeniously prevented them from bowing outward under the considerable weight of the roof. Each rafter was meticulously cut to ensure it rested firmly against the top plate, with the lower end notched to sit squarely on the oak plank. The rafters were intentionally spaced 24 inches apart, closer than what was typical for frontier construction. This tighter spacing was crucial to distribute the roof's load evenly, preventing any single rafter from concentrating excessive pressure on the straw bales below, which could lead to compression and structural instability. This deliberate spacing also provided ample support for the wooden sheathing, which would ultimately bear the weight of the final roofing material. The hip roof design demanded precise calculations of rafter angles and lengths. Each rafter was carefully angled to meet the top plate at 30 degrees, creating a roof slope steep enough to efficiently shed rainwater and snow, while remaining shallow enough to minimize resistance against the relentless prairie winds. Constructing the 4 hip rafters that formed the roof's corners required compound angles, a challenging feat that Jonah mastered by crafting templates from scrap wood. These templates ensured that each corner of the roof shared identical geometry, resulting in a cohesive and structurally sound design. As construction progressed into October, the fierce winds of the Sandhills region became an increasing concern. These winds, often reaching gale force, could generate tremendous uplift forces on roofing systems, especially those with large overhangs or steep slopes that acted like sails, catching the wind and potentially tearing the roof from the structure. Traditional cabin construction frequently failed when wind forces exceeded the holding power of nails or pegs used to secure the roof to the walls. Jonah implemented several strategies to minimize wind vulnerability. He limited roof overhangs to a mere 6 inches on all sides, just enough to divert rainwater away from the walls without creating excessive leverage during windstorms. The hip roof configuration also helped to reduce wind resistance by eliminating the large, flat gable ends that were characteristic of many frontier structures. These gable ends often caught crosswinds, creating destructive stress concentrations that could compromise the roof's integrity. The roof-to-wall connection system drew inspiration from shipbuilding techniques Jonah had learned from his uncle, a carpenter who had honed his skills in Philadelphia shipyards before moving inland to become a farmer. Each rafter was secured to the top plate using a combination of a notched bearing joint and a wooden peg driven at an angle through the rafter and into the oak plank below. This dual connection provided exceptional resistance to both uplift and lateral movement, creating a robust mechanical bond capable of withstanding wind forces from any direction. Board sheathing was applied diagonally across the rafters, with each board running from the top plate on one side to the peak connection on the opposite side. This diagonal pattern created a triangulated network of strength, preventing the roof structure from racking or twisting under wind loads. It also provided a solid base for the final layer of cedar shingles. The boards were secured with square-cut nails driven into pre-drilled holes to prevent splitting the wood. The completed structural system faced its first major test during a November windstorm, which brought sustained winds of 40 miles per hour, with gusts exceeding 60 miles per hour. The storm struck at night, awakening families throughout the region with the sounds of loose objects being hurled against buildings and the ominous groaning of structures straining under the intense wind pressure. At the Holbrook Place, the wind caught the extended eaves of their gable roof, twisting the entire structure and pulling several rafters loose from their connection points. The northwest corner of the roof lifted and slammed repeatedly against the remaining structure, causing significant damage. Tom Brennan spent the night holding interior doors closed against the wind pressure that found gaps in his sawhouse walls, while outside, his roof lost 12 shingles, which scattered across the prairie. In stark contrast, the Bale house weathered the storm without any discernible structural movement. Jonah meticulously inspected the building throughout the night, finding no signs of stress or displacement in any part of the roof system. The hip design effectively shed wind from all directions, while the continuous top plate distributed the loads evenly across the walls, which remained plumb and solid. When morning arrived, the structure showed no damage beyond a few shingles that required minor repositioning. More importantly, the walls themselves had proven capable of supporting the structural loads without the compression or buckling that skeptics had predicted. The top plate system had successfully transferred roof loads into the Bale walls while maintaining the thermal integrity that made the building system viable. The compressed straw had behaved like solid masonry under load, demonstrating that organic materials could provide exceptional structural strength when properly configured and supported. By December, the completed building had demonstrated that unconventional materials could achieve structural performance equal to that of conventional construction, while offering superior thermal efficiency and utilizing locally available resources. The integration of foundation, wall, and roof systems had created a unified structure that responded to environmental stresses as a cohesive unit, rather than a collection of separate components fighting against each other. The winter of 1902 arrived early and stayed late, bringing a sustained period of extreme cold that separated successful homesteaders from those who abandoned their claims and retreated to the relative comfort of towns. By January 15th, temperatures had remained below 0 degrees Fahrenheit for 18 consecutive days, with nighttime readings plummeting as low as 28 degrees below zero. Snow fell almost daily, creating drifts that reached the eaves of single-story buildings and making travel between homesteads nearly impossible for weeks at a time. This was the ultimate test that revealed the full potential of Jonah Miller's innovative building system. While individual components had proven their worth during milder weather, the extreme conditions of this winter demanded that foundation, walls, and roof work together as a unified thermal envelope capable of maintaining human habitation under conditions that pushed conventional structures beyond their limits. The continuous cold created thermal stresses that exposed weaknesses in buildings throughout the region. At the Holbrook Place, Repeated freeze-thaw cycles opened new gaps between the wall boards as the wood contracted and expanded, while frost buildup on interior walls indicated that heated air was escaping through joints that had seemed tight during construction. The Gunderson sod house developed ice formations along the base of interior walls where ground frost penetrated the inadequate foundation system, rendering the lower portions of their single room uninhabitable. However, the sustained cold also revealed the thermal flywheel effect that made Jonah's thick-walled system superior to conventional construction under extreme conditions. The massive bale walls stored heat during the brief periods when the stove burned actively, then released that stored energy slowly over many hours, maintaining interior temperatures even when fuel supplies ran low or families slept through the night without tending fires. This thermal inertia became crucial during a 10-day period in late January when blizzard conditions made it impossible to venture outside for additional firewood. Families across the region were forced to ration their remaining fuel supplies while hoping that weather conditions would moderate enough to allow resupply trips to distant timber sources. The Brennan family burned furniture and interior walls torn from their sod house to maintain minimal heat, yet still suffered interior temperatures that dropped into the teens during the coldest nights. The Miller family faced the same fuel shortage, with dramatically different results. Starting the crisis period with only 2 days' worth of normal fuel consumption remaining, they reduced their stove firing to one brief period at midday and another before bedtime. Even with this severe reduction, the interior temperature never dropped below 42 degrees Fahrenheit, warm enough to prevent water from freezing and maintain conditions suitable for normal household activities, including cooking and basic washing. The performance differential became measurable through direct comparison with the Holbrook family, whose frame house occupied a similarly sized footprint on comparable terrain, just 2 miles away. During the coldest week of February, with outside temperatures averaging 15 degrees below zero, the Holbrooks maintained an average interior temperature of 28 degrees while burning 1.5 cords of cottonwood. The Miller family achieved an average interior temperature of 51 degrees while consuming only half a cord of the same fuel type. These results reflected the compound advantages of proper building system integration. The elevated stone foundation prevented ground frost from conducting cold into the floor area, while the thick walls reduced heat loss through conduction and convection. The hip roof design eliminated the thermal bridging that occurred where gable-end rafters penetrated conventional wall systems, and the continuous top plate prevented air infiltration at the critical wall-to-roof junction. More significantly, the building maintained its thermal performance without degradation over time. Many frontier structures showed declining efficiency as gaps opened, joints loosened, and materials settled or shifted. The Bale House demonstrated improved performance during its second winter as the compressed straw continued settling into tighter configurations, while the lime plaster cured to increased hardness and weather resistance. Word of these results spread rapidly to families throughout the region through the informal communication networks that connected isolated homesteads during the long winter months. When travel became possible again in March, several neighbors made specific trips to examine the Miller house and discuss the construction techniques that had achieved such remarkable fuel efficiency under extreme conditions. The first serious inquirer was Heinrich Zimmermann, the farmer who had supplied the original bales and had watched the construction process with skeptical interest. After spending an evening in the warm interior while outside temperatures remained below freezing, Zimmermann asked detailed questions about foundation preparation, wall construction sequence, and plastering techniques. By April, he had begun construction of his own bale house, modifying Jonah's design to include a larger kitchen and additional windows while maintaining the essential thermal and structural principles. The adoption process accelerated when the local Lutheran congregation decided to construct a new church building in 1904. Faced with the high cost of importing sufficient lumber for conventional frame construction, the building committee invited Jonah to present his bale building methods as a potential alternative. The resulting church building used load-bearing bale walls 2.5 feet thick, creating a worship space that could be heated comfortably with a single wood stove even during the coldest Sunday services. This church construction project, completed in 1905 and used continuously for over 20 years, demonstrated that bale building techniques could produce structures suitable for public use and capable of long-term durability. The building required only routine maintenance, consisting of annual lime wash applications to the exterior plaster and occasional replacement of damaged shingles, costs that remained far below those associated with frame construction of comparable size. By 1910, at least 12 bale houses had been constructed in the immediate region, with the techniques spreading to other areas of the sandhills as homesteaders shared information about materials and methods that could provide comfortable shelter using locally available resources. The practical advantages of reduced fuel consumption, lower construction costs, and improved comfort levels during extreme weather had overcome the initial skepticism about using agricultural waste products for permanent construction. The broader significance of this innovation extended beyond individual building projects. The successful adaptation of organic materials to structural use demonstrated that frontier families could achieve housing standards comparable to those in more developed regions without depending on expensive imported materials or specialized craftsmen. The techniques required only basic carpentry skills and tools that most homesteaders already possessed, making improved housing accessible to families operating on limited budgets. The integration of traditional building knowledge with locally available materials had created a sustainable approach to shelter that worked within the environmental and economic constraints of Great Plains settlement. The method succeeded because it addressed the specific challenges of the region, rather than attempting to impose construction techniques developed for different climates and resource bases.